or we will be in a second. All right. I do believe we are live. So, hello everyone. We're going to get started in a few minutes here. Just give us another 2-3 minutes, both for everybody to get in and for us to finish a couple last minute things. So, just sit tight.
We are live yet or no?
Yes.
Yes. Fantastic. All right, everyone. We're just going to take a handful of minutes here to let everyone kind of settle in. So if you're looking to get some popcorn, get a refill in your glass of water, now would be a good time. And we will start shortly.
Hey, Corbin.
Right. That now seems like a good time to start. Right. So welcome back to the University of Minnesota's Universe at Home. Tonight, I'm going to be your main presenter. My name is Corbin Condon. I'm an astrophysics major here with the University of Minnesota, and I also study French. We'll let both of my colleagues introduce themselves as well.
Hi there, everyone. My name is Ethan Rothholtz. I'm a physics and astrophysics major. I'm going to be your coordinator for tonight.
Hi, I'm Daniel. I will be going through our discussion activity towards the end of the presentation. Yeah. Hi.
All right. Fantastic. So we will start.
Oh,
so one. Actually, oh, yeah.
So, Gary Borgs has a question. It might be good to tackle this a little later, but I thought I'd bring it up now. Did quasars mostly develop during the early evolution of the universe?
We'll talk about that during the quasar section, if that's all right.
Yeah.
So we'll come back to that one. If we don't recall during the questions after the quasar period, please do just resend the question. But to start, one of the things that brought me personally to the field of astronomy is the unparalleled sense of scale. The sheer size of objects and distances is absolutely astonishing. But what I really mean to say with all of this is I like big number. I can't personally speak to the opinions of my colleagues, but for me, big number is fun to work with. Now, from the idea of big number, there's a lot of biggest numbers we could talk about in astronomy. We could look at the most massive stars, or the most populous galaxies, or even the most empty regions. But today, we're going to talk about the brightest lights in the universe, quasars. Now, I can assure you right away, quasars are a specific type of more common celestial object. Now I'm going to wait like a minute or so and see if anyone wants to try to guess in the link or in the chat if anyone if what common more common celestial object quasars form around. After a minute from about now, we'll just go ahead and present or go through. Otherwise, feel free to take some guesses.
Gary has got a guess of black holes, while Caleb Mitchell has a guess of stars.
All right. Well, moving from there, Gary got it. Well, I mean, you're both I'm sorry. For quasars specifically, Gary is correct. It's black holes. Oh, I'm sorry. I was supposed to change my slide there. Black holes. However, Caleb is correct as well in that accretion disks, another topic of tonight, we do form around stars. Well, I guess I should say more so that quasars are black hole adjacent. Quasars are actually active galactic nuclei. These are around a central supermassive black hole found in almost all galaxies. These regions are just truly extreme. And tonight, your and my understanding will depend upon knowledge of black hole accretion disks, like we just mentioned, so that we can understand quasars better. And, well, in turn, understanding accretion disks hinges upon understanding angular momentum. So in order to get to the more tantalizing and, in this case, literally flashy astronomy, we have to begin a bit more humbly with angular momentum. So what exactly is angular momentum and why does it matter? Well, why it matters makes a bit more sense after we've established what it is. So let's start by trying to understand what angular momentum is. And unlike the unit and physics 1 classes, we're not going to spend multiple days going over all the specific calculations. I promise you this. It's best to begin understanding angular momentum by comparing it to linear momentum. Linear momentum is a bit easier to understand, and I would describe it as the feeling of how if you're running really quickly, it's kind of hard to just stop suddenly. Or maybe more understandably, if you imagine a semi-truck that's speeding down the freeway at 65 miles an hour, it doesn't really like to suddenly stop moving. On this slide here, I have an example of a Newton's cradle, or, well, it's a CGI Newton's cradle, in which it's easy to see the momentum transfer to these spheres. The reason that moving objects generally want to keep moving is because they want to conserve momentum. I'm choosing the word conserve very specifically here because this whole idea is associated with a conservation law in physics. This is a very cluttered slide, but it'll make sense. A conservation law is something that, as a system evolves and changes down with time, in our example, the truck drives down the road, another one is a planet hurtling through space, the conserved quantity won't change. There are conservation laws for linear and angular momentum. There's conservation laws for energy, and on the slide here is a conservation law for mass. In this case, this is more of a chemical example, but it's easy to understand. So we have here set up in a flask on the left side, a chemistry experiment about to happen, and we have a reactant dropped into a mix, and then you can see that after the amount of mass in the flask is the same. This is because the mass is being conserved, much like momentum and angular momentum when we eventually get to it. So because linear momentum is easier to visualize, I'll start with an example. Imagine a person in a small rowboat on a lake with their boat floating still in the water, like in this regrettably low resolution image. If this person throws a large stone out of the boat in one direction, that's going to be seen right here, moving this direction, the boat will conversely start to move in the opposite direction. That's this angle, or this arrow right here is representing that. This is because for the system, in this case, it consists of a boat, the person, and a stone, the total momentum is conserved. The whole boat, person, and rock system wants to keep its initial momentum, which was 0 because it wasn't moving at the start. So when this person throws a rock in one direction, the rest of the system moves in the opposite one to fully cancel out the two momentums. Now, this brings us to angular momentum. And this is another cluttered slide, and for that, I'm also sorry. But for angular momentum, what's conserved? Well, with linear momentum, the conserved quantity depended upon the mass of the object and the velocity of the object. For angular momentum, we are going to instead use these quantities here, the moment of inertia and the angular velocity. Oh, I just accidentally misclicked. Okay, there we go. Both of these have an appropriate analog to linear momentum as well, from you can see on the slide. Moment of inertia is comparable to mass, and angular velocity is comparable to, well, velocity. In this sense, for the linear case, the object's mass can be thought of as an intrinsic property for it to resist acceleration. And this is exactly how moment of inertia works. It's this object's intrinsic property for it to resist angular acceleration or beginning to spin. A one-bladed ceiling fan or a wheel awaken will have this. And actually, even that one can of Chef Boyardee from the commercial where the kid in the store wants to get it, but then their parent says no, and then the can rolls all the way after them home, that also has a moment of inertia. On the other hand, angular velocity is how quickly the spinning object will spin over its entire circle. You can measure linear velocity in something like miles an hour or meters per second, but conversely, angular velocity is measured in angular degrees or radians per second as it spins. Now that I've gone through this somewhat cumbersome definition, what are the main takeaways we need from angular momentum for our talk tonight? Well, two specific ideas that I'll visually demonstrate in a little bit. Firstly, from the formula, we can see that angular momentum depends upon angular velocity, though we already talked about that. Angular velocity as a term depends on two things: radial distance from the center of motion and its linear velocity here. Let's go back to that centrifuge visualization. In this, here the cockpit of the centrifuge is a distance from the center equal to the radius of this object. And the cockpit, at any given specific instant, is going to be moving directly forward at a given velocity. We already covered how angular momentum needs to be conserved, which means that if we want to lower our instantaneous linear velocity or our radius, we must increase the other to conserve the angular momentum. This will be demonstrated with our good friend the squeezatron shortly. The other aspect to understand is that angular velocity has a direction. On the slide here, this is represented by the red arrow pointing leftward. That's going to be right here. This does not want to change. This wants to stay in here, and that's part of the conservation of angular momentum. However, this is a bit wonkier to explain, so we're just going to cover this visually. Now, I promise that this is the last thing before we get to the cool space stuff that you all came here for. But understanding angular momentum is important to understand accretion disks. So we're going to go over some visual demonstrations to solidify our understanding of how angular momentum works. But because of some of the policies in place, I am regrettably unable to give these demonstrations live. So we will instead look at two pre-recorded demos that I made with the help of my good friend and University of Minnesota physics demo room assistant, Elizabeth Ochoa. To set this up, I do have to stop my stream. So you're going to be greeted with one of my colleagues' smiling faces. And I just have to reestablish this. Oh, right there. All right, Dan, Ethan, is this looking good? Can you see?
Yes, sir.
And we'll start the demo.
Hello, it's me, your main presenter, but from the past, relative to you now watching this. So I mentioned when we were doing our demonstration on angular momentum that we were going to use a demonstration with our good friend the squeezatron. This is our good friend the squeezatron. So I'm going to explain how this thing works so that we can then demonstrate the principle that I had explained earlier. So the squeezatron is made up of two very massive spheres attached by lever arms to this system here, and this entire mechanism here can freely spin like this. Now, the squeezatron is also made up so that most of the mass resides in these spheres and not in these lever arms. So you can approximate this as actually two spheres orbiting a central area to some degree of accuracy. Additionally, you'll notice that there's a lever here. When I squeeze on this lever, this contraption will pull down, pulling this down and bringing the spheres inwards. This will, and so if we compare that really quickly, here to here, the idea here, I talked about how when we were conserving angular momentum, this thing moves a lot. When we were conserving angular momentum, one of the quantities that could change within was the rotational velocity needed to stay the same, which meant that if we wanted to increase or decrease the radius, the linear velocity, or how the sphere is moving in this direction or in this direction, will need to go up. And so you can see here that since this can freely rotate, and that I can control it here, the radial distance, we should be able to see that if this is spinning and I squeeze, it will have its spinning will go up. So if I spin this like this, and then I squeeze, you can see that it dramatically increases in terms of how quickly it's moving. That is the property that we are trying to demonstrate, and it's something that you may have seen if you watch professional figure skating, where individuals will have their arms outwards and then pull them inwards to reduce their radius. Though I won't be doing that. All right, and now it's still me from the past bringing you a second demonstration. This is one of my favorite demonstrations in basically all of physics. So here I have a bicycle wheel with a twist crank so that it can freely move in this direction, but if I move it in this direction, you can see that the bicycle wheel will spin. On this side, I just have another handle and a rope. This rope will make sense once we begin the demo. So, I had mentioned that spinning objects have a direction. So if I spin the wheel like this, based on the diagram we went over, the motion is in this direction, which means that the angular velocity vector, which you don't have to understand clearly, points in that direction, points out that way. And that's the thing that really wants to stay the same. So if I don't, no, my rope got messed up. If I don't spin this at all, this is gonna work a lot like you'd expect. If I just hold it like this, it will fall down to gravity. This makes sense, and this is what you'd expect. However, if I instead start to spin this, and it takes me a minute to get this going to a sufficient speed, this vector is now in play, the angular momentum vector. And so now, if I hold this up, you can see that it does not drop down. That vector wants to stay straight. However, obviously we live in a gravitational field of Earth, and so you can see that it does droop down over time as friction and gravity take their toll on this system, but the principle remains. And that was a really good example of this demo. What was that noise?
All right, fantastic. And so I apologize if there was some inconsistencies in my grammar during that presentation. I have only one take to make it. And so I did just kind of have to go freely. However, I'm just going to get this back up here as we get the slideshow back on. So demo video is too large for the slide. Sorry about that. And now we have finished the section on angular momentum. So we're going to take a small break, maybe 2 or 3 minutes, to answer any questions so that we can move forward with a clear understanding to talk about accretion disks.
All right, so we do have a couple of questions. Caleb has a question on quasars, so I think we will tackle that one once we talk about quasars. But he also asks, does a perfect circle have a moment of inertia if it has 0 radius? Certainly an interesting question.
If it has no, I'm going to say this, if it has no radius, then it would not be rotating about anything, so it would not be capable of rotational motion. I think. kind of looking to Dan and Ethan on this one to back me up, as they are both also in the same programs that I am studying this material.
Zero radius would, well, if you want to take it extremely literally, zero radius would imply there's nothing there, so there would be nothing to rotate, I would think.
That's also how I'm interpreting this. In the case of a perfect circle, if you want to think of it as a loop or a ring, then yes, it will have a moment of inertia. We won't be discussing a lot of the many formulas for moment of inertia, as there are quite a few, and they're all a little bit more in depth than we would like to get for this presentation tonight. I'll wait for about another minute on my end before we'll begin the next section.
I do think that we can answer Caleb's other question right now. So you asked, how do we know how bright, how do we know that quasars are so bright? What if they're so close? And like the answer to that is that we can use something called standard candles in astronomy. You can actually measure the luminosity of another object and use that luminosity, the flux that you measure at Earth, which flux is just saying how bright you are measuring at Earth over some area per unit time. You can use the flux that you measure from a star, or in most, like the standard candle is some things called Cepheid variables. So you can measure those and measure their brightness, their distance, and then determine, based on how bright they are, determine how far away something else is given its brightness. Or, yeah, you can do comparisons between astronomical objects. Another tool is something called redshifts. I don't know if we cover too closely redshifts.
We don't cover redshifts in this talk, no.
It will be something that can answer Gary's question later. Redshift is essentially an astronomical distance, and also used as a time with Hubble's constant. And so redshift tells you like how redshifted, how distance an object is, and we can measure the spectrum of the object and determine how far it is based on how redshifted its spectrum is.
Yes. Okay, and so now we can return to the main presentation from this question break. And now it's time for the promised space stuff. This time we're talking about, oh no, unfortunate. Hello, okay, what's happening with my slide? I'm gonna just reload this. Sorry about that. We were here. Actually, we were here. Fantastic. We are talking about accretion disks. Accretion disks are structures formed by diffuse gas and dust orbiting around a central body. Disks can form through a number of different means. The only defining feature of an accretion disk is that the material of the disk loses both energy and angular momentum as it moves towards its central gravitational body. For young stars, the material comes from the surrounding nebula the star formed in, pulled on by the growing gravity of this maturing star. I'm sorry, for other objects like black holes, their disks typically consist of material taken from other objects orbiting the black hole. The gravity of the black hole slowly strips material from other objects, in the most extreme cases, tears them apart completely, and forming disks of material. Oftentimes, someone might associate accretion disks with black holes, but the majority of accretion disks actually form around protostars as protoplanetary disks. Additionally, it is believed that type 1a supernova are the result of a binary star system between a white dwarf and any other type of star, where the dwarf will slowly strip away material from its companion star. As it does this, it will eventually accrue enough material to temporarily reignite itself, at which point it will create a type of supernova that is extremely consistent. So much so that it's considered a standard candle of astronomy, much like the other one that Dan had talked about during the question period. regardless of the central object, the physics and properties behind these structures remain the same. This is to say that an accretion disk around a black hole and an accretion disk around a protostar are going to be very similar physically. The properties of the central object mainly influence the frequency of light emitted by the disk as it orbits its host. These emissions come from a combination of frictional and gravitational forces acting on the material inside of the disk. Friction between dust particles causes the material to slowly spiral inwards towards the central body, where gravity acts to compress the dust particles and further increase the friction between them. This causes dust to both fall faster as it approaches the body and heat up as it gets closer, resulting in the photon emissions that I had mentioned just a bit ago. Typically, the emissions of disks around stars are centered in the infrared region, while emissions for more gravitationally intense objects like neutron stars and black holes are centered in the X-ray region, both of these in the electromagnetic spectrum. The reason for this difference in emission frequency lies in the physics of the disk itself, this interior portion, as opposed to the cloudy region farther out. The energy of each photon is derived from the gravitational energy lost as this dust particle, the bits from these clouds, move closer to the central object. And as such, objects with more intense gravity tend to create more intense emissions. However, there's another component of this disk's motion that we must account for: the disk's angular momentum. Like all objects, the total angular momentum on the disk must be conserved, that is, from here outwards to the edge. But at the same time, dust must lose angular momentum to fully fall into its central body. So the question becomes, how is angular momentum conserved? And as it turns out, angular momentum lost to dust falling in is gained by dust farther away from the object and not yet falling in. This, in effect, means that the angular momentum is transported outwards from the central body. The action of pushing angular momentum far away from an object had no explanation when models of accretion disks were first derived in the 1940s. It was initially discovered that this action is based on what is known as the Rayleigh, I'm sorry, am I saying that right, Dan? You know. Rayleigh criterion? Rayleigh criterion. I'm glad that I had you correct me. The Rayleigh criterion simply states that the viscosity of the disk plays a part in the inward motion of the gas, and thus the emission of these photons that we've talked about. This did not explain how angular momentum was transported, and a model known as the alpha disk model was created using turbulence-enhanced viscosity, a lot of big words, to explain this redistribution. The source of turbulence was not clear when the alpha model was proposed in 1973. Thus, the theory required a free parameter. And a free parameter in physics is something which cannot be predicted mathematically and must instead be estimated with theory and experimentation. This free parameter was designated alpha, and it is used to build the model. While successful in some respects, this model made several assumptions which, on top of its inability to determine this alpha, limited its usefulness in the long term. It wasn't until 1991, just about 30 years ago, when a new mechanism was proposed to explain the transfer of angular momentum and do away with this alpha. This mechanism, known as the magnetorotational instability, which is a lot of syllables, proposed that in an accretion disk, the presence of a weak axial magnetic field I'm sorry, I just lost my place in my mind. The mechanism, which was the magnetorotational instability. I'm sorry, yes. This mechanism proposed that in these accretion disks, the presence of weak axial magnetic fields between two neighboring molecules will act as 2 points connected by a massless spring. This spring creates tension. So if we imagine this, it's going to be two particles, and there's an imaginary spring made up of magnetism between the two of them. And the spring creates tensions as these molecules move closer to the body, because as you recall from the demo with the squeezatron, as they move closer, the one moves closer, it will have to move farther and it will pull them apart. And this will increase tension in this theoretical spring. And as this tension grows, the inner molecule is forced to slow down under this force, which reduces the angular momentum and as it pushes into a lower orbit. But this lost momentum is then transferred to the outer molecule, pushing it into a faster orbit until these two molecules are too far apart to keep interacting. The magnetic field required for this action is believed to be caused by dynamo action, the same type of action which creates planetary and solar magnetic fields, much like our Earth's and our Sun's. While the majority of magnetic fields in this process are very weak as material falls into the central body, some of these magnetic fields can become anchored to material in the disk. This causes magnetic flux to concentrate around the central body over time and creates significantly stronger fields as a result. Since the material is orbiting the central body, this causes the magnetic fields to follow this motion and create a poloidal or torus-shaped magnetic field in the inner regions of the disk. In the most extreme cases, these fields are responsible for the final thing that you'll likely associate with accretion disks: plasma jets shooting out along the poles of the central body. But I don't want to spoil the final topic too much, and so we're going to take a break again for questions.
Alrighty, so we've got a few more questions from Caleb. The first two are
enthusiastic.
The first two are focused on the demo videos that you showed, so I'm going to go over those first. First of all, Caleb asks us, could we use a wheel rotating to propel ourselves?
I'm not sure what he means. I would like if Caleb would rephrase that question again. And once he gets that one rephrased, until he gets that one rephrased, let's move on to the second question.
Okay, I'm guessing this also refers to the wheel demo. He asks, would the wheel demo have worked better without friction?
So both of the demos would have worked theoretically better without friction. The Squeezatron is set up such that friction plays a very minor role in it. What would have happened with the wheel hanging on the rope with no friction and no gravity is that, as you recall, it was at a right angle to the rope that I was holding. It would just have kept rotating in a circle there until, without any friction, it just wouldn't have stopped.
Okay, and then the last question that Caleb asked us is, how can angular momentum be transferred without any means of contact between bodies? He says that he doesn't really understand how dust particles could be magnetic.
Ethan,
Now,
you did a little bit more of the research in the area for the accretion disks and this method. Do you want to take this question? Or?
Yeah, I can take a stab at this. So the first thing we have to recognize is that that particular action that we were discussing is more prevalent with high mass objects like black holes and neutron stars, because they generate a much higher gravitational field. If you remember what Corbin had said earlier, objects with higher gravity are able to produce higher temperatures than objects with lower gravity. Because of the higher temperatures, black holes in particular can actually turn gas and dust into plasma, and then that allows the particles to start interacting through forces like magnetism, whereas the more inert dust particles might not have been able to. And that allows for magnetic interactions between particles, and as Corbin had explained earlier, the magnetorotational instability process that we discussed earlier. So if that's still unclear, please let me know. I can try to describe it further. But Caleb did restate his first question. He says, the wheel resisted gravity. If we were in a vacuum, would we have moved in a direction?
The wheel, so would me, the person holding it? I haven't thought of this. Sorry, okay, so I think I misspoke earlier on when I talked about gravity. Without friction, if there were no friction, the wheel would have kept moving. What was interesting about gravity in this case is gravity kept the string tight, which freely let the wheel fall down. And this is what allowed it. And then gravity wanted the wheel's, how do I say this? Vector for angular momentum to point downwards, because that is the ideal rest form for that system. However, because the angular momentum didn't want to, I guess, what's a good word for this? Just give up that term. That's what kept it kind of like straight up at that right angle relative to the rope. And so we do need gravity for that example, as that wouldn't quite work in a zero gravity environment. I may have misspoken earlier when I answered the previous question.
Okay, then Caleb has another question. Yes, if the only thing that can be interacted with is plasma, how can the dust begin moving slower? Wouldn't the dust just stay at the same radius, as it would be unable to lose angular momentum? One thing we should mention, Caleb, is that there are a couple other processes which I believe Corbin is going to discuss, which also impact the angular momentum, particularly with more gravity focused interactions. So there are other pieces to some of this, which we probably should have mentioned, or at least mentioned earlier. But the magnetism section is one of the bigger pieces. So
okay, and now let's head back in to the presentation. And so now it is time for the titular topic, quasars. If you'll recall, the way that I introduced quasars was as the brightest lights in the universe. In the past, before 1964 specifically, these objects were simply known as quasi-stellar objects. However, in a 1964 paper, American astrophysicist Hong-Yi Chu used this term, quasar, and developed, in my opinion, one of the best tasting words in contemporary science. However, here and now, just a moment ago, you might have noticed that I described these objects as quasi-stellar. This is to say that these things appear as stars, but later on were found not to be. In the far-flung past, it was more or less assumed that these pinpoints of light were stars, and it wasn't until the more contemporary period of astronomy that these were discovered to be discretely different objects. But how so? If you see here, I have a stellar spectrum and a quasar spectrum. I don't know why I said quasar. Quasar spectrum. The left one being the stellar spectrum and the right one being the quasar spectrum. These spectra measure how common and how many times we see light coming in at a certain energy or wavelength on the bottom axis. It is important to note that the stellar spectrum here begins at 4,000 angstroms and goes up to 8,000, whereas the quasar has a lot more of a gap. So what we're really comparing here starts about here and ends about here. It's this region. So what is important and how are these graphs distinct? I'll start by mentioning the quasar graph. You can see these sharp spikes coming up. These are here, but specifically in our range here and here. These are more huge spikes of certain wavelengths being churned out by these quasar interactions that we talked about in the accretion disk. This is to say that you can visualize the spectrum as, I'm sorry, I don't know why I said that. Now, we'll instead focus our attention on the stellar spectrum now. You can see these huge dips here, 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 and here. These are called absorption lines. This means that the light particles being emitted by the nuclear fusion in the star's core will pass through and outwards, except for specific wavelengths. That's these ones. This is because more or less these the atoms that make up the star are hungry for these wavelengths. And so if you ever take a spectrum of all the colors of a star, you're going to see specific holes. Now, these absorption lines are entirely absent from the quasar, and this is how we knew that they weren't exactly stars and why we started to call them quasi-stellar. So now we understand how these brightest of lights became a curiosity. So what exactly makes these lights so bright? We know that for stars, like our sun, they fuse material in a nuclear process in their core. This gives off huge bursts of energy from this reaction. Protostars, alternatively, have immense pressure and glow from their thermal radiation. Now, the latter one of those seems relatively reasonable as a case for what happens in accretion disks and specifically quasars, but protostars are extremely dim compared to these objects. So what brings about this brightness? The answer is relativistic jets. So this image I have on the screen here, this central object, this bright point, if you'll actually recall, I'm sorry, this is the the active galactic nuclei of M87. And M87 is actually the object that 2 years ago we had managed to first take a photo of a black hole of. Then you'll see that there's a lot of kind of diffuse kind of grayishness. This whole region out here is the elliptical galaxy at play. This stream of blue light that's incredibly long is the relativistic jet. So the question then becomes, how through can the material that's being brought in closely in these accretion disks be flung so vigorously and forcefully outwards and so close to the speed of light? Well, there are two theories being talked about right now, but I will focus on the one that I perceive as simpler, and this is called the Penrose process. So the Penrose process only applies for Kerr and Kerr-Newman black hole models, which more simply put means black holes that spin. These spinning black holes are embedded in a space-time region that is very confusing. Within this area, that's going to be the area that these lines are drawn in and outside of this sphere, within this area, it's actually entirely impossible to remain motionless or to stand still. To be a little bit hand-wavy about this, the general relativity of these systems says that these massive spinning black holes actually drag and pull the space-time around them, much like a whirlpool. So any nearby material will begin to start moving in the spinning direction. And these effects become stronger as we get closer to the event horizon, where you would have to be moving the speed of light in the opposite direction just to stand still. The region where we are outside of the event horizon of the black hole, but inside of this space-time whirlpool, is called an ergosphere. Right here in this diagram, we have the inner horizon, the outer horizon, and the ergosphere. So the ergosphere, this dynamical region, is from the edge of the outer event horizon and just kind of up to a finite place. Or at least that's how the models are built. This is called an ergosphere because it's a sphere that does work, with ergo being the Greek term or Greek prefix to mean work. I mean, it's not exactly a sphere, but it's a close approximation for physics. So let's talk about the material from our accretion disks undergoing a Penrose process. Let's pretend that we have some imaginary rock. And when this rock enters the ergosphere, it will be split up into two pieces. We can then set up the motion of these two rocks carefully, such that one of them will fall into the event horizon and be consumed by the black hole, and the other one will continue onwards and out of the ergosphere to escape. This escaping piece will actually have a greater mass energy than it entered with. This is because, again, with the careful setup, the piece of rock that fell into the black hole actually has a negative mass energy. Now, this seems like it may destroy the conservation laws that we talked about earlier, but in actuality, this extra mass energy from the escaping rock is being paid for by the black hole when it absorbs or consumes the other rock. Of course, you may notice that I did mention how we do need to carefully arrange for this whole setup, and that does make it seem like this wouldn't happen very often. But on the scale of galactic nuclei black holes, so much material constantly falls into them. This is actually an extremely common occurrence. This is how the inward falling material is shot outwards with such vigor. If you'd like to look more into it, the other process I had mentioned is the is the Blanford-Zolcic process. And this is actually a specialization of the Penrose process. However, this involves magnetic physics, plasma physics, and general relativity together, so it's a little bit beyond the scope of this talk. But to circle back for an important note, these relativistic jets of plasma and superheated material primarily emit their photons or their light in a certain band of the electromagnetic spectrum. Specifically, this is the radio band of the spectrum. This means that we couldn't actually see these objects with a telescope in our eyes, even though they're incredibly bright. However, I've deprived you of cool space photos for a minute, So let's return to quasars. So, quasars, these cosmic forges that consume and destroy stars around them, pulling in dust and planets and creating these massive Saturn-like rings. And they spit out their material along these relativistic jets at the speed of light along their polar axes. Yeah, they're pretty cool and fun stuff. However, it might occur to you that this implies these incredibly bright lamps should only be visible. Should only be bright when you look at this jet, and you'd be correct. Such an object's designation as a quasar, in fact, depends upon its orientation relative to us. So, if a quasar's jet points perpendicular to us, much like us looking at this particular diagram on the left, we just won't even see this as being this bright of an object. We'll still see the relativistic jets as more so lobes that we can discuss later on during the activity, but they don't quite look the same. This is because these lights are being obscured by the clouds around their accretion disks. Earlier, we called these toruses, or this diagram calls them dusty toruses. Now, ideally, we call these quasars if their jets are at an angle of Earth of anywhere from about 75 degrees to 10 degrees. Much like if we're looking above here and downwards, this is at an angle of probably something like 30 degrees. However, this begs the question of, what do we call these things if they're pointing directly at the Earth, like in this right image? Well, we call these Blazars. I personally think this artist rendition is an extremely impressive, and I love its presence. It looks just powerful and awe-inspiring. But I will be entirely honest with you. There's not much else of a difference between quasars and blazars, except for how blazars are directly pointed at us. So instead, when we're talking about blazars, let's circle back to the first thing I mentioned tonight. Big number. The brightest blazar yet recorded is a big chain of letters and numbers. 3C454.3. That is right here in this image. This quasar has an apparent magnitude, the way that a lot of astronomers measure brightness as we see it from Earth with our eyes, is an apparent magnitude of 16. Now, in all honesty, that's not a terribly impressive number. Magnitude works with golf rules, so the lower your magnitude is, the brighter the object is. And a difference of one number on the magnitude scale corresponds to about a factor of 10 in brightness. This is to say, if I had something of magnitude 1 and something of magnitude 0, the apparent magnitude 0 object would look 10 times more bright to me from the Earth. So to scale this, this brightest of blazars, which has a apparent magnitude of 16, most planets have a magnitude of about 0 to us. And the Andromeda galaxy has a magnitude of about 3.5. So what makes this kind of huge magnitude number impressive? Well, something else with a magnitude of 16 is Pluto's moon of Charon. Charon is about 3.2 billion miles away from us at the Earth. That's approximately 35 times farther from us than the Sun is. However, 3C454.3 is 7.7 gigalight years away. That's almost 17% of the way to the edge of the observable universe. To be a bit more fair, we can talk about absolute magnitude. Still, recall that this is for quasars, this is in the radio spectrum. And absolute magnitude is, instead of how bright things look to us on Earth, it's how bright something looks from 32 light years away, or 10 parsecs away. This blazar, 3C454.3, has an absolute magnitude of negative 31.4. Our sun to us on Earth has an apparent magnitude of negative 27. This means that at a distance 2 billion times farther than we are from the sun, this blazar appears to be 1,000 times brighter than our sun. Quasars and blazars are truly some of the most extreme objects in our universe, and calling them impressive isn't doing them the justice that they deserve. And now, finally, before moving on to our activity, which Dan will lead us through, we'll stop for questions for the last time tonight.
Alrighty, so we've got a couple. First of all, from Zoe H, we have beyond the fact that they have a different orientation, is there a particular reason blazars are differentiated from quasars?
No, there's not. So they are studied and specifically focused on as an astronomical object because looking directly into this cosmic barrel gives us unique insights into relativistic jets. But beyond this, the only thing that is really different is, like I said when I was talking about the magnitude of their brightness, is just the big number.
All right, and then we're going to turn back to Gary's initial question at the beginning. Did quasars mostly develop during the early evolution of the universe?
So, yes and no. Quasars are a result of active galactic nuclei, which were more active during the earlier universe. As galaxies form, a lot of material will collapse down into the center of them because that's what gravity likes to do most of the time. So when and then that's when these supermassive black holes in centers of galaxies will form. This occurs in all galaxies, except for maybe irregular ones, in which case they are unique to the point that we should talk in a different. I'm sorry. What did I just say? I just lost my train of thought. So supermassive black holes are, for standard galaxies of spiral or elliptical situations, they can be active galactic nuclei, and a lot of these did form in the early universe, yes. Quasars continue to be active, though, as long as they are being fed material, which never stops happening in galactic cores.
All right, next up, Caleb asks, could quasars support...
Sorry, Dan was about to talk.
Yeah, my computer's being slow right now. To answer in more definite terms as far as timescales for quasars, I believe the age of active quasars is basically over. You'll find the most quasars between 9 and 11 billion years ago, I think, and some of them up to 13 billion years ago.
Yeah, so it's the idea is that as long as these supermassive black holes are being fed enough material that they are considered active galactic nuclei, they will continue to be turned on. And most of the ones that we see, like Dan said, occur at a certain distance in the past. So we are over the peak of quasars running, but we can still see quite a few of them. And most of these supermassive black holes were forged in the early universe. Ethan, you were going to introduce a new question.
Yeah, Caleb asks if quasars could potentially support life if they were at the correct distance.
So there's a lot of more nuance to this question, but realistically, not human life, because the peak emissions in the visible spectrum that we depend upon and the infrared and ultraviolet are just not there to support us. However, if you're talking about astrobiology, a lot of things can happen a lot of different ways. And so I don't want to definitively say that life couldn't form around radio light, but it's unlikely. And this is also because planets don't tend to form and exist on their own without moving relative to a distant quasar, being that quasars are objects of different galaxies.
All right, we've got a couple more here, and then we should probably move on. First of all, Gary asks, when galaxies merge, could you see a quasar from that?
When galaxies merge, could we see a quasar? So when galaxies merge, their supermassive black holes at their cores will fuse into one larger. This process will very likely accrue a lot of material around the newly forged supermassive black hole, the creation of the two previous ones, and this will likely create an active galactic nucleus in the case that neither one of these was previously active and was instead just the central supermassive black hole. In this case, you could see a quasar form, but it would likely take time because galaxies never merge I shouldn't say never. They very, very rarely merge directly onwards like plates. And so it'll take a moment for the dynamics of this accretion disk to form and start picking, so as to speak, the direction that these relativistic jets will move or shoot or fire. I'm not exactly sure. Dan, do you know the verb?
Oh, I have no idea.
All right, we're just going to go with fire.
but AGN's active galactic nuclei are believed to be mostly formed from mergers,
Yes.
And quasars need to have active galactic nuclei, so it's pretty good to say that they'll.
Yes.
Alrighty, so next up we have a question from Dick Hendrickson. He's asking about photon and neutron spin. Don't photons and neutrons have spin? What happens when they are pulled apart into quarks as they near a black hole?
So, as one note, photons cannot be pulled apart into quarks. They are a more unique type of. I mean, I guess I'm not exactly a particle physicist, but this is my understanding: is that they are not made up of smaller particles. Is this the case?
Yes, they're made of packets of energy but they're not made out of physical quarks.
I do want to clarify that he did say protons and neutrons.
Oh, I thought I heard photon.
I'm sorry. I misread that as photons.
Oh, you did say okay. Okay,
yeah,
so
I
protons and neutrons.
Okay.
I'm sorry. As these protons, they do. You are correct. They do have spin, which is more or less an analog on the particle level to a larger angular momentum. What happens when they are pulled apart into quarks as they near a black hole is that these quarks still do have their own spin intrinsic to them. This is described by the Standard Model, which I am not familiar with. If either Dan or Ethan know a little bit more about me.
One note is so protons and neutrons, they're held together. Their quarks are held together by the strong interaction, strong force. So in order for them to break apart into quarks, you need the gravity of the black hole to overcome that force. And typically, when you pull apart and separate a quark, the energies you have to expend to pull them apart will create another quark, and they'll just form another pair.
Yeah. Basically, physics actually does not allow individual quarks to exist on their own. Anything that separates one quark from the other quark it's connected to just creates more quarks. So anything that would pull apart a proton or neutron would just end up creating new pairs of protons and neutrons.
Not necessarily protons and neutrons.
Well,
but
yeah,
pairs.
not necessarily those exactly, but to pull apart a proton or neutron, you have to create another atom in its place, because you cannot have a single quark just existing on its own.
Not necessarily atom, just another quark.
Well, point being, quarks are not allowed to be on their own. Okay, we have one last question from Caleb, though. So, could a quasar use any object as mass, or any object with mass as fuel? For example, could a quasar use another quasar as fuel?
So this was sort of covered when we talked about galactic mergers, because quasars do need to be come from active galactic nuclei. So the only time that a quasar could assimilate a second quasar would be during one of these fusions. I'm sorry, galactic collisions. And likely when we have two previously or recently collided pairs of galaxies. So we have two which fuse, and then those two fuse. In this case, I don't know that it would be accurate to say that these are using, that one quasar would be using the other as a fuel. It's a bit more accurate to say that the dynamics at play will eventually settle out to a new quasar or a new supermassive black hole, which has a larger reservoir of material to pull from.
Okay, on that note, I believe we are good to move on.
All right, so fantastic. I'm going to hand over the presentation to Dan now to go over the Zooniverse activity.
And thanks everybody for their questions. They're very informative.
Oh, hi everyone. 1 second. My laptop is starting to die, and when I was charging it, I was starting to get cut out because it's overheating. But I've turned up the performance, and let's see how this goes. I'm going to start sharing. Ethan, I believe, will be providing a link to our activity in the chat. I would ask if everybody can see this, but I can't tell. Can anybody else see this?
We can see, yes.
Cool. So on the topic that Corbin had discussed today, we're going to be looking at and doing an activity with Radio Galaxy Survey on Zooniverse. Now, if you're unfamiliar with Zooniverse, Zooniverse is a citizen science project. So essentially, scientists provide, create work with Zooniverse and create activities and other science like interactions for community people who aren't necessarily scientists, and help them do real science, help make their jobs easier. And one of the big cool things about Zooniverse is it's very applicable to everyday citizens. And if you do enough Zooniverse projects and enough data collection and analysis, you can end up on a paper. You could be named as a, I don't know, maybe co-author. And in particular, we're going to be looking at just one of the activities that Zooniverse provides. It's called the Radio Galaxy Zoo LOFAR. As you can see from here, you'll be looking at potentially some jets, some active galactic nuclei. And as Corbin mentioned in the presentation, a lot of AGN provide activity in the radio band, and jets are seen in the radio band, not typically the visual band. So we're going to go through this activity on Zooniverse, and you're going to be able to classify, again, potentially classify some jets or other radioactive phenomena. So we're going to start by going through the tutorial. I'm going to guide you through it, and then you'll be able to go and do the associate and identify on your own, and while we're here, and identify some real science, some real data. So I'm going to press this tutorial. First, actually, if you haven't used Zooniverse before, make sure to create an account at the top. You can see I'm already signed in. You should be able to create one and be able to do the activity. So this particular project provides you pictures of a visual, like an optical photograph. On top of that optical photograph, they provide radio contours, which you can find. So I'm clicking these three buttons here to go between visuals. So you can see here, this is a picture of a radio jet. You can see the two lobes, but in the visual, you can't see the two jets. You can actually see its active galactic nuclei here. And then if you press on the first picture it provides you can see the contours of that radio jet. I'm going to go through what you can do with the Zooniverse project, but if you would like a reminder afterwards, or if something I say is not clear enough, you can always press tutorial and go through their nicely created tutorial program. So what we're going to do is we're going to take a picture at this one, and this is a very nice picture. I was actually hoping it would show this one, because again, it provides two jets. And you're going to be looking, and you're going to be looking at this solid elliptical. You can notice that there's one solid elliptical and a lot of dotted ellipticals. I should say also, make sure to ask questions in the chat. We're still connected to the chat in case anybody has questions. And anyways, a solid elliptical line and a bunch of dotted elliptical lines. And what Zooniverse and what the scientists running the program want you to do is to look at the ellipticals and decide, hey, do these dashed ellipses match the same source as what the solid one's indicating? So the solid ellipses is indicating this here. And if you're unsure, or if you later have a more challenging one, don't worry too much. Go through the project, but it will bias and check you against other people who conduct the experiment, conduct the activity on the same image, and you'll be able to bias out any errors that may have been made. But anyways, what you're going to do is you're going to say, hey, this dashed ellipse and this dashed ellipse, they kind of look like they belong to the same source as this solid ellipse. So you're going to press for the first one, for this component selector. You're going to press and you're going to say, okay, this ellipse is inside it, is connected to this one, and this ellipse is connected to this one. So we're going to press these two ellipses. We're going to check. During the tutorials, it'll allow you to check. It's pinging me wrong because I tried confirming the elliptical one inside the solid one, I think. So I think it got confused. Yeah, I accidentally marked this one. Oh well. It's the tutorial. It's fine. And the next question is going to ask you, once you've pressed confirm, is going to ask you where the host galaxy is. The contours can be pretty difficult, so it might be best to just press optical. Look at the radio. Hey, 2 lobes. Maybe it's in the center here. Go back to optical. Hey, there's a source there. So you're going to press that, and that to me looks like the host galaxy. And what I'm seeing here is an active galactic nuclei that is propelling 2 jets in opposite directions, as anticipated for a jet source. So you're going to press that. You're going to say, hey, there's my source. There's my lobes. These are connected to here. And you notice I didn't mark any of these because to me, these don't look like they're part of this source. These just seem like, other maybe active galactic nuclei out there. And then you're going to press next again. Hey, and it confirms in the tutorial that was the active galactic nuclei. Good to go. And then it's going to ask you some questions. If you're confused on these questions, if you're confused by what they mean by these, or if whether or not what you're identifying is an actual source, you can always press the field guide, and it provides you a lot of useful information, a lot of fun, a lot of help. So I'm going to press none. I don't see anything wrong with this image, so done. And then we've got another one. You can go through this, go through all the tutorials. It'll tell you which ones you've already done, and then when you're done, you can always go back to the main page and do associate and identify to see other real data. This time without the tutorial, it'll be a little bit more challenging, I imagine, because it won't provide you that helping hand. But hey, so I'm going to go ahead and just click these 2 as another example. I think these 2, if it's identifying this as one source, I'm going to identify those 2. And it looks like, yeah, that's probably what it means. And then bright and radio, not visual. I don't see much there, but I'm going to press next. Check the contours one last time. I personally am not seeing it. It's not apparent to me. Perhaps it's here or here. But anyways, I hope that was insightful, and I hope we're going to give you a few minutes here, 5 or so minutes. Feel free to go through some exercises on your own, identify some data, and let us know if you have any questions.
Feel free to ask any other questions you might have about the presentation as well.
And of course, if you do decide to head out, then hey, thank you so much for coming by tonight and listening to the talk. But we will be here for a handful more minutes just to answer any questions.
I'm going to go ahead and stop sharing my screen. Hope it hasn't been taking up anybody else's, but
All right, and with that, we haven't gotten any questions, I don't think, in the past 3 minutes since the end of the activity. So we will finish up here for the night. And thank you so much again for coming to Universe at Home today. Again, as always, 2 weeks from now, there will be another presentation, and we'd love to see you back for that one. Thank you so much for your time.
thank you.
Thanks for coming, everyone. Have a good one.